Okay, so back to the theorem here. So the Fermat theorem in calculus 1, we can also using that in the partial, with the exception that the partial, we are going to have another function and let the one of the either x-axis or y-axis, they are going to be constant, and we are deriving and basically says that this will be similar to what we have in calculus 1. So we, for example, we state that the y is a constant, so we are going to derive with respect to x. So we are going to say that g prime at point A, this will be 0. So we say that, so we derive, because b or y acts as a constant, so we can treat them as a constant when we derive. And then we can equal that to 0 at A, and this will be the critical point. And this is to proving that this is going to be true as well. Okay? Because when we partially derive with respect to x, we treat y as a constant. When we partially derive with respect to y, we treat x as a constant, which is basically saying that this is actually, if we have another statement for another function, this is just a normal single variable like in calculus 1. Okay. Okay, I think maybe a little bit not practical, but let's see if we have examples, okay? Just to see and showing how it works. Okay. So let's say we have this. Okay. So, okay, we have an elliptic parabola. So this is an ellipse, and this is a parabola. If we cut from every aspect here, we get a parabola here, and we get a parabola over there. So zy and zx is a parabola. Okay, we have partial x, we have partial y, which is basically we just deriving for each one of them. For x and y, we have this two, and if we take the taking the critical point, or maybe let me write first here. So this means that the point, so here, point AB is critical point. Or sometimes we call a stationary point. So this is true when this point, when we partially derive, they are going to be 0, or if one of partial doesn't exist, we can say that this is going to be critical point as well. Okay, and based on this, then when we take this equal to 0, which means 2x minus 2 equals 0, so x will be 1, and then 2y minus 6, this will be 3. So the only way we have a critical point is only this point, 1, 3, which very clear. You see this point here, as this is going to be the local or the minimum value. But if you are not given the picture, you can also try to compute this 1, 3 into the functions and see what will be. So for example, if we take this into completing the square, we can get this. So plus 1 and plus 9, so plus 10, so plus 4, right? And this is going to be, we can say the x minus 1 squared is going to be greater 0. This also the same. So we have the fxy should be greater than 4, at least. So therefore, this is a local minimum. So of course, this is something that is basically analytically observations either through the visuals or through some calculation and proving whether this is going to be minimum or maximum. Of course, in practicality, we have some other methods that can directly compute the minimum and maximum that I will show you after this page. Okay. So it's much more practical. Okay. Now, if we see another conditions, let's say we have another function. Suppose that we have this function here. So this is what we call as a hyperbolic paraboloid. And this is how it goes. I think I mentioned this in chapter 12, several parts and additional videos. How we can get this is actually a parabola. So if we rotate, this is like a saddle, or horse. So this is how we sit on the top of the horse, right? And in the middle, we call it the saddle point. If we clearly see what the saddle point means, it doesn't show whether this is, because at this point, it can be this or it can be that parabola. So if you can see, it can be that way, it can be this way. So what is this? Is maximum or minimum? It is not both of them. It's called the saddle point. Okay? But the way we calculate this, it's also critical point. Okay? This is also a critical point. So here we have the one that's called the saddle point. Okay, so if we try to find the partial of this hyperbolic paraboloid, let's say partial x, we can have negative 2x, and then partial y, we have 2y. The only possible critical point is just 0, right? 0, 0. So the only possible way is 0, 0. So if we take y equals 0, so at y equals 0, we are going to have a parabola negative x squared, which is, it is going to be less than 0 if the x is not 0, right? And for x equals 0, this will be y squared, which is a positive parabola, right? And this will be it's going to be positive, and if this is the y it's not 0. So this means that point 0, 0 with these conditions, it cannot be maximum or minimum, right? Cannot be extreme value. Because at the point 0, 0, this will be maximum in x-axis, but minimum in y-axis. And you can confirm through your visuals, this is positive parabola, this is negative parabola, right? Okay. So this name as a saddle point. So to determine whether the point is minimum, maximum, or even saddle point, it's better if we are using different tests, which we call the second derivative test. So the test is actually we are going to have, so if we have existing second partial derivative of a function, which are the function need to be continuous, and then in certain domains, and then suppose that the partial x is 0, partial y also 0, and that is the critical point. And we can let this formulations, if you see the formulations, we call the D is actually from the determinant. D is equal partial xx, which means the second partial derived with x and then derived with x, and partial yy derived with y, derived with y. So this is the order how it's going to be derived. Okay? And then this is partial xy. And remember, deriving x and then deriving y will be the same if we deriving y and deriving x, resulting the same. Okay? So this minus this squared. Or in another way, if we write in the determinant in the metric system, so D is, if you remember, if we take this A, B, C, D, this equal to AD minus BC. So this D can be written as fxx, fyy, this is fxy, and this is fyx, or they are the same. Right. So maybe we can write this first as a note, because this will be true for every requirements that it has. This will be true. So if D is positive, so the whole thing here positive, which means suppose that we have the defined AP, we determine the AP, we know the critical point. It can be more than one, it can be maybe 2, 3, 4. Okay? So we have some critical point. So we need to test the critical point. So test every critical point. If when we put here, the calculations become positive, we can have this two possibility. Okay? So testing the positive, and then testing the partial xx. Actually, it can be partial y, but let me just using this partial xx. Partial xx, put the point, test the partial xx. If this is positive, this will be local minimum. If this is negative, this will be local maximum. Okay? And then, if D is less than 0, it must be saddle point. No need to test the partial x. It must be saddle point. So either D is positive, negative. So when it's negative, it would be saddle point. If it is positive, it can be minimum or maximum. Okay. But if if we have the, because it doesn't mention here, if D is equal 0. If D equals 0, so no information. No. So we need to make sure it is positive or negative. So if D is 0, the test gives no information. It could be local max, it could be local min, or it could be saddle point. So no conclusions. And yeah, this is to help you write down the D. You can write as a determinant like this. Okay. And I hope you get the idea on the determinant. Basically. Anyone have learned matrix before? Or who hasn't learned matrix before? Who hasn't learned? Who haven't learned matrix? So if you see this, do you understand? Or no? No? Okay, good. Okay, you need to try to catch up. So this is what we call the determinant. In matrix, we goes by, so this is like a tools, like operation tools. How we make it is basically, if we name is A, B, C, D, this will be cross multiply and then subtract the other cross multiply. Okay, so that's how it goes. So that's the determinant. Okay. If you take later the engineering of mathematics, you will learn a lot of matrix. And I'm not sure if you are familiar with the MATLAB. It's actually computational tools that is easily solve matrix system, matrix equations. And all the differentials that we learn in partial derivative or even in the calculus 1 derivatives, they are all can be written in a vector system or in a matrix system with the same context, but in matrix system. Just to let you know that we can write in any way we want. All right, and maybe just a quick example, okay, before I go to the next part. Quick example on this. How to use it, okay, basically. Interesting, right? But when I look at this is like a draw here. Like a Patrick Star. Okay, anyway, that is the functions. And if we draw this, is looks like that. So first thing, every time the question asking about local minimum and maximum, we can partially derive, find the critical points. Okay, so first is partial derivative. So we can write here partial derivative. So we can check partial x. So deriving for all x components, so for x cubed minus 4y, and all y will be 0 and constant will be 0. And then we get the partial y. Okay. And then this is the first thing, and then the second is critical point. So taking the partial, each partial equally to 0. So taking this equals 0, and we get the the equation that can be substituted. Okay, so sometimes we don't really get the exact number within the first equation, but we have two equations that we can solve. So we can have the other part as well, and we can simply write down this as two equations. So we have two equations, and hopefully we can solve this. Okay? Either you can substitute y to that part, or substitute the x to this part. Okay? Each one of them we can have a similar results. Suppose that we have y is equal x cubed. So I will try to substitute this to here. So y cubed will be x cubed and then cube. So this will be x with power of 9 minus x is 0. So yeah, it's higher power. So x is x power 8 minus 1 equal to 0. But this part we can factorize. Okay, it's just simply just like a quadratic functions. We can let the power of 4 okay, and this part we can also factorize. Okay, and we can skip this part, right? This is imaginary, so we can get, or if you want to write completely, let me just write again, and this will be x plus 1, x minus 1. So the only way we have a real value is this x, x plus 1, and x minus 1, right? So we have x is equal 0, or maybe let me write one by one. X is equal negative 1, x equal 1. Right? We have three x's. Okay, and we know that the x is equal y cubed. Okay, so when x is 0, y is 0. When x is negative 1, y is also negative 1, right? When x is 1, y is 1. Okay, so we have all these pairs, all these critical points. So this is critical point. Okay, and then next, after we get the critical points, what we can do is we can maybe write down the second partial. We can start from partial xx. So partial xx, we can derive a partial x. So 12x squared. And then partial xy is negative 4. And the partial yy is 12y, sorry. 12y squared. And then I think it's best to write as a table. So you can start, this is A, B, this is your point. And write down the D. The D is partial xx, partial y minus partial xy squared. So each one of them, we need to put the points into the each equations and then just compute, okay, and check whether it's positive or negative. Okay, check 0, 0. We check 0, 0. So partial xx will be 0. This is also 0. So this is 0. This is negative 4 squared. It's positive. But it's negative. So it's negative, right? So this is, what we need is just the sign. So this is negative, which means that this is a saddle point. No need to calculate the other part of that. Okay. So this is a saddle point. Okay, now check negative 1, negative 1. This will be positive 12, also 12. And then multiply with 144, positive. And then minus 4 squared, so this becomes 16. So positive minus 16, it's 100, negative minus 16, still positive, right? Still positive. So we need to have a evaluation on the partial x-axis. The partial x-axis is 12x squared. We check negative 1, it's become positive, right? That means we have these two local minimum as we predict in the picture, right? So this is local minimum. So this will be, this is positive, and suppose this is partial x-axis. This is nothing there. So here is positive. So we call this is a local minimum, right? Okay, this is the same because it has a quadratic, it's a square, so it must be the same with 1, 1 as well. So this is also positive. If you can see the picture here, so this will be the saddle. This two must be local minimum. Okay. Okay. Okay, so if you're interested in finding how we get this formulation for D, it's actually from directional derivatives, but I think I just show you how it goes, but not completely. So we start with the directional derivatives, which is the del f, and then we have a unit vector, let's say u. Okay. We are going to, or maybe let me expand this partial x. Let's say h. So let's say u is hk. So basically, we are going to differentiate one more time. So differentiate one more time. So we get du squared f, which means this is the second directional derivative, will be equal to du f. So we use the operations in directional derivative twice. This will be giving you partial x of du f h plus partial y du f k. And if you solve this, you will get the partial xx in between, partial xy and everything here, and you will be giving the connections to our d. Okay, I don't think we have time for that, so I think I will leave it as it is. Or let me just write, just to skip some process, and this will be partial xxh plus partial yxk h plus partial xyh plus partial y k, and then multiply k, and this will give you partial xxh squared plus partial 2 partial xy, because they are the same, and hk plus partial yy k squared. And then we can rewrite this, factorize the everything here, and taking the complete square, actually what we are care about is the last part here. Okay, this is the one that we follow. Okay, now, but what I think what we emphasize on this chapter is how we could determine the local minimum and local maximum through the or saddle point through this method, okay, using this table here. Okay, let me give you another point of view, and this is basically just summary of what we have. So when we talk about the absolute max and minimum, we are going to get into the exactly for the functions. If they have certain domains, then we need to also check the domains. Okay, so similar to what we have in calculus 1. So basically, absolute maximum, if it is the highest possible within the condition that we have, absolute minimum is the lowest possible, right? And then if we bounded the function of two variables in some domain, then the domain itself will be also need to be evaluated, whether it is also maximum, also minimum, or maybe they are in absolute max or min, right? So basically, when we have this, so we first, similar as before, as the previous one, find the critical points, find the extreme values, okay, for each one of them, and then the boundary also. So find the values on the critical points, and then compare with the values in the boundary. Compare all of them, And then the largest one will be the absolute max. The lowest one will be the absolute minimum. I think no problem at all. Basically, this question is just adding the domain as your evaluations to be compared with which one is the maximum and minimum. Okay. Okay, some example here is, I think we can focus on the example. Okay, it's more practical. So we have this function of two variables x, y, and we have the domain in the rectangular 0 x3 and 0 y2, which we can visualize this in rectangular shape. So perhaps this is the rectangle. So this is D. So then the first thing, we find the critical point. Okay, so we take the partial x and equaling to 0, and partial y equaling to 0. And then we can solve this. I think we can solve the first one here, which is x is 1. So when x is 1, y also 1, right? So 1, 1 is the only critical point. And the value of f11 is 1 minus 2 and then plus 2, which is 1. Okay, I think we can break for a while. Okay. Okay, let's continue. Okay. So to find the absolute maximum and minimum, we need to include the rectangular D, the domain. Okay. So for example, if we name this line is line 1, line 2, line 3, line 4, we can observe that on line 1, so L1 is when dy is equal 0. So for L1, y is 0, so we have differences on x. So we can say that, and then we can plug in the informations that this will be only x squared, which is from 0 to 3 on the x-axis. So this is an increasing functions, and the minimum value, so the minimum value is the f00, which is the smallest value on this L1, which is going to be 0. And max value will be 3, right? The x equal 3, I mean. So this is going to be f30, which is going to be 9. Okay. And we're going to evaluate all these segments and check their maximum and minimum. Okay. So check again here for L2. This is x equal 3. So we have 3 and y. Y is going to be from 0 to 2. And now we have 3, it's 9. 3 squared is 9. So minus 2, 3 is 6. So 6y and then plus 2. So 6 minus 6 plus 2 is 4. So minus 4y. So mean value is F30, or perhaps this is the max. Or we can say that this is a decreasing functions. So the mean value is actually 3.2. So we just put everything inside. So this will be 1. So max value is F30, which is 9. In the first one, I forgot to mention this is my increasing functions. But basically, what you can do is you can just check the points all the way you want and find out which one is the highest and which one is the smallest. It's the same thing. This is more what I did here is basically more detailed and more structured. We can take the L3. So L3 is y will be equal to 2. So f x2, this will be x squared minus 4x plus 4. And then x will be from 0 to 3. And since this is, we can rewrite and solve this or factorize, make it into a complete square. X minus 2 equals x minus 2 squared. We can see that the minimum value is when x is 0, or 2, sorry, x equal 2, which is going to be 0, and max value is this. Okay. Where is the 0, 2? 0, 2 will be also max value. Right? And then lastly, we can have the L4, which is x is 0. So we only have y. So 2y. And this will be 0 to 2. And we can say the max value starting from the 0 to this is 4. Mean value is 0. So from all this, we see that the maximum value possible is 9. The minimum value is 0. Okay. So absolute max value is F30, which is 9, and absolute mean value is F00 and also F22, which is equal to 0. But actually, for practicality, if you are writing down in exam, what you are going to do is basically testing every point possible. So testing for every point, no need to write in like a detail like this, but if we write like this, it may be helpful for your observations. But basically what you're going to do here is check the critical points, check its value, and then check the domain for every possible x and y. Okay. And check everything and then decide which one is the maximum, minimum, okay. And then which one is the absolute max, absolute min. Okay. And basically that's it for maximum minimum value and also the absolute max and minimum. So it's basically not really much in description, but perhaps you just have to be familiar with the method, especially the second derivative test when we take the d. Okay. So I hope you can get familiar to that. I have some exercise after this. And then the other part is, the last part in chapter 14 is what we call as Lagrange multipliers, which is actually a one unique method to solve the maximum minimum value. Okay, perhaps we can see some exercises. I will leave that to you to try to check and solve. But let me go for introduction on the Lagrange, and we can review all of this maximum minimum value and also Lagrange next week for overview. Okay, you can see some, maybe observe some particular questions. For example, if there are only this function without any domain, which means that this is standard finding critical points, maximum, minimum, local max, local min, using second derivative test. Okay. You can try, maybe take one or two functions that is maybe simple enough. Just try the method first. Okay. Try the method. And another part of the questions that can be is about the absolute max and min. You see the differences in the absolute max and min. They gave you the domain or the restrictions. Okay? Which one has the, for example, has this 3 points here, triangular region that you can try, or you can get the exactly which x and y interval that you can try as well. And another part of the questions is this kind of question here. Find the shortest distance, blah, blah, blah. Find the points that are closest to the origin, blah, blah, blah. This is also maximum minimum value problem. I will try to review this next week, okay? But now, let's move to what we call as a Lagrange multipliers. Okay, so Lagrange is a special method to solve the max and min value. So suppose that we have a functions f, and then we could determine using level curve. So we equaling the function with some constant, and then try to see in the picture or in the graph where is it in two dimensions. So we are viewing from the top. Imagine that this is actually a surface like this, but we are viewing on the top, and all this line, the blue line, is every part of the projection of the surface for each one of the constant. Okay, like maybe you are observing some top view of the maps. This is like a mountain maps that they have different contour, right? Okay, so you have this lines, the possible lines, right? And then in Lagrange, we are going to have this other function we call function g equal to also a constant. What we are going to do, we are going to equaling this g with this f, which in terms of, if you remember, the del of the function, that will be the perpendicular, right? So we are going to equaling that g with f, and we are going to find the multipliers between those two. That multipliers we call Lagrange. Okay? So let me write, okay, to make it easy. So we want to find this value of the extreme. So we need to find extreme values of f, right? And then we have the g. We call g as a constraint, okay, or restrictions for this f actually. So we seek the extreme value of f when point xy is restricted by the constraint, or restricted to lie on level curve the constraint g. So the constraint will help us to determine the extreme value. Okay, now to maximize the f xy subject to the constraint g, or let me write f with also maybe blue. Okay, it means to maximize means find largest value of a C such that level curve fxy equals C intersect, or let me write with the blue. So this will be intersect exactly with the constraint. So intersect means touching each other. These two functions will be touching each other, which means their normal line, both normal line, will be the same or identical. What is the normal line? The normal line could be described as the del. So the del f will be parallel with the del of g. So that's why we can write an equation that states the del f at certain points will equal the del of g at certain points, but of course we will have some multipliers between these two. So there will be some ratio or a number or scalar, which this is what we call the Lagrange. Sometimes we write the Lagrange as lambda. So this is a Lagrange multipliers. So Lagrange is a scalar. So the requirements for the Lagrange to be worked is we need to find the constraint. We need to have the constraint first. If not, then we are not able to find anything. So the only way you can do is, if you want to find the extreme value, find the critical points, find the max, mean, saddle point, like we did before. But if it is giving you the constraints, some other level curve that we can approach with our original functions, that means we can find the relation between these two, which means that when it's intersect, the normal line will be the same. Okay, if you see from the picture here, the idea is normal line will be there, this red one also the same normal line. So the del between those two will be the same. Okay, which means this is going to be true. So basically, remember the goal. Our goal is finding the extreme value, which means in the process, when we try to solve these equations, maybe we are going to find the lambda first, or maybe we are going to find the point first. Depends on the equations. It depends on the equations. But at the end of the day, all of this, what we need is the points for the extreme value. Okay, in practical, how to use this method? Okay, maybe if you want to write here, this is more official statements. Okay, so we find to find max or mean values subject to the constraint, the level curve G, assuming that the value exists. That's our assumptions, and the del G is not 0. And then find all values x, y, z such that it is going to be multiply by this lambda, and then we can evaluate all the points x, y, z that we get from 1. The largest will be the maximum, the smallest will be the minimum. Okay, as simple as that. Okay? So first maybe take it the example 1 here. Okay. So first is we see that exactly that this f is the one that we need to find, right? That's the original function. And the circle, this will be our restriction, or will be the constraint, right? So we can write first maybe the constraint as g. Okay, that's our g. And we can write the del f equal lambda del g, which means basically it's stated that for every partial x for f will be equal to lambda partial from g with respect to x. The same thing with partial y. And do we have partials? Oh no, we only have 2 variables. Okay. And we have the constraint g xy is equal 1. Okay, now start with the partial x. F will be 2x equal lambda, the partial g, x is 2x, right? And then this will be 4y, lambda, this is 2y, okay. And we have the restrictions x squared plus y squared equal 1. Okay. Or maybe let me write this in here and maybe giving to the left part. If we solve this, we can factorize 1 minus 2 or 1 minus lambda. So this can be x is 0 or lambda is 1 to make this happen. And all possibility we need to check. So we can check if x0 it's give you the y is plus minus 1 from the restriction from here, right? And if lambda is 1, then it is giving you 4y equal to y, or the same thing with the x. If lambda 1 is, let me just write here, is equal to y. So 2y is equal to 0, so y is 0. And when y is 0, so x squared will be equal to 1. So x will be plus minus 1. Okay. So we have some pairs, and I think we can we can write all of that. So we can write that 0, 1, and 0, -1. That's from here. And this one is 1, 0, and then -1, 0. Okay, so we have 4 points. Okay, so you need to put every possible points for from our calculation here. We need to determine all possible points that we get. So for example, here is x can be 0 or lambda is equal 1. And when x is 0, if we see the restrictions, the constraint functions, that y could be plus minus 1 because of y squared here. Okay? And for lambda 1, we could check from this, and it turns out that y is 0, and when y is 0, x could be plus minus 1. So we have, when x is 0, it could be 1 or -1. When y is 0, it could be x equal 1 or -1. So we have 4 points. And then the next step is we check every point here, put all into the functions. The one that is largest will be the absolute max, the one is minimum will be the minimum. Okay? So check all the points. So check the f01. What is the point? So fxy is x squared plus 2y squared. This will be 2. So f0 -1 is also 2. f10 it's 1. f-1 0 is also 1. So this will be the max value. This will be the mean value. So this is how it looks like if you want to see in more visuals. So this is the point, the minimum, this is the maximum. So this is the surface, it's an elliptic paraboloid. And when you project this to the xy, if we project through this point here, it should be an ellipse, but since we restrict this circle as our constraint, then we are going to have this as a circle. If you see from the top, you see that this is an ellipse and the circle is here. So basically, this blue line is our possible level curve for each one unit, and the circle is we approach and then make sure that it is touching the level curve at some point, and basically the normal line will be the same. That's why we take the del f equal del g multiplied by del lambda. Okay. Okay, any questions first? So basically first is finding the partial for each f and the constraint g. And then after that, solve the equation. Solve the equation, it can be solving the lambda or solving and get the point. It can be any possible way, but the idea is we need to get this point out of this process. Okay? Okay, let me check is there any, oh yeah, we can also have this kind of questions as well. We might have, like for example, we have a rectangular box without a lid is to be made from some cardboard. Well, it's like a problems in the optimizations, but now we have a partial derivative problems, which we need to derive a partially, right? So suppose that the volume of the box, let's say we want to maximize the XYZ, but remember our constraint is 12 meters squared, and the box is without a lid. So if you take the box like this, and suppose that this is X, Y, Z, the top will be empty, right? So no top, which means that this will be 2xz plus 2yz, but only xy, because xy only 1, right? This need to be equal to 12. So this will be the constraint. So this is a similar method. This is our goal. We need to maximize or minimize this function. This is our constraint. So first we can take the del for each one of them. So del v and the del of this constraint. Let's say this is g. Let's just write that as g. Okay. So we can safely say we are going to del this 2 and equaling in a Lagrange multiplications. So partial v with respect to x will be equal to lambda gx so vx will be yz. This is lambda, and then gx partial g 2z plus y, right? And then do for all parts of the other y and z. So this is vy, gy, this is xz, this is 2z plus x, right? And then phi z equal lambda gz. This is xy, 2x plus 2y. Okay, now we need to solve this. And there are many ways to solve, but if we see this part here, each of them, if we multiply, for example, this, if we multiply with x, and this multiply with y, this multiply with z, we are going to get the xyz formulations, right? So for example, if we multiply this with x, this will be xyz, and this is 2xz plus xy, okay? And this multiply with y will get you to this. Okay, and then multiply the z to this one. So how to solve technically is basically based on your math experience. Okay? I don't have any specific patterns how it's going to be solved because there are many possibilities. Okay? So it's based on you actually. Okay, now we have this, and remember we have the constraint. So we can write, for example, the 2xz to yz is this, which means that this is 12 minus xy, right? We can substitute. Or we can solve directly this part here. So because of the same xyz, they are all the same, so we can solve the formulations and write, for example, 2xz plus xy is equal to yz plus xy, which gives you that this is can be cancelled. This is xz equal yz. But since z is not 0, because if z is 0, it will be, the volume will be 0. So x should be equal to y. Now, the same thing here, from 2yz plus xy and 2xz plus 2yz this will give you 2 2xz and xy. So y is 2z. So x equal y equal 2z. We have the restrictions as 2xz plus 2yz plus xy equal 12. So we can exchange everything to z. So x will be 2z, so this is 4z squared. So this is substitute. And 2y will be 2z, so 4z squared. And xy is 2z, 2z is 4z squared is equal 12. So this will be 12z squared, and z will be 1, okay? So we are ignoring the negative because if negative, no meaning in the real applications. We want to make sure that this is positive. Okay, so this means that here, x, y, z all positive, okay? So when z equal 1, x is equal to, y is equal to. So the only way that is going to be having this volume is basically by taking this 2, 2, 1. It's 4. Okay. So this is for constraint 1. Okay, so we have only one constraint. We can have more than one. We can have two constraints. So we can have del, two dels for the constraint as well. I think that will be for, I think, next week. I think I will just end until here. Okay. Maybe any questions for this part? Overwhelming. Overwhelming, right? I guess so. All the process here, right? Okay. It seems like lost connections. It's still finding the server. But anyway, how to process this actually can be many ways. But basically the one you need to think is, you need to connect everything. Connect everything from the constraint, connect everything from all this equation here. Because if you have like this part here, we can start with maybe changing the yz using the constraint g. We have also yz here. Then we can substitute and maybe it can help you to solve. But I don't think so because it has 2, this is only 1. Or maybe you can multiply by 2 to remove the complications. But actually it can be many ways. Like this 2z plus y, if we multiply, it becomes this. This is, we can also substitute this with this, right? 2xv, xy, so this will be 12 minus 2yz. Maybe that will be helpful. So all of them we can substitute, and then we can also make it equal. But I think it will result in the same conclusions, in any way you can see. Some equations maybe requires you to find the lambda value first, and then put the lambda value, and then check the x, y, z value, and then check the value of the functions. It can be, this is practically depends on how you can solve linear equations. So it depends on your math experience. I want to say that. So it means every possible question that you might have, you need to try. I think next week I will try to review and give you one more additional Lagrange, because Lagrange can be 2 constraints. So this is only 1 constraint. Right? We can have 2 constraints. So the del can be two like del f equal lambda del g, and maybe the other one is not lambda. We call it Lagrange 2. Maybe mu del h. We can have 2 Lagrange values. Much more complex, much more complicated. Okay. So I think that's for today's class. Okay.